Okay, so hello, and thanks for coming to the colloquium again. Yeah. I have a great pleasure of introducing Dr. Jeremy Gunawardena as today's BioMech colloquium speaker. Dr. Gunawardena has used math to investigate various biological systems, in particular cellular signaling. Indeed, when I was a graduate student at Michigan, I actually studied his paper a lot. And actually still his PNA's paper was one of my favorite theory paper. And actually I didn't know that, but I found that he got a PhD from Cambridge with the major of algebraic topology. And then, but now he's a faculty of systems biology at Harvard University. So it's a big transition from the topology to the system biology. So his most recent work and topic of his talk today is following the energy in cellular information processing. So please join me in welcoming Dr. Gunawardena.
Jay, thank you very much for that introduction. And I'm really sorry about the confusion over the time of the talk. We managed to lose track of the fact that summer was over and winter had started. And,
yeah, it's horrifying, yeah.
But thank you all for coming back later than you had expected. I very much appreciate that. It's a great pleasure to be able to talk to you. And I just had a few minutes of hearing a little bit about what some of Jay's students and postdocs have been doing. And it covers a lot of ground. I'm going to talk to you today about a direction that we've been exploring in my lab for the last few years, largely in collaboration with one of my colleagues in the department. I'll explain that a little bit down the road. And it has to do with the role of energy in information processing. I think we're all familiar with the fact that energy is essential for biology. And we know that you can't do things like move or make patterns without energy. That's very well understood, but the role it plays in information processing is not so clear. And that's really what I want to discuss with you today. Okay. So, what I'm going to talk about is roughly the topics that you see here on the screen. I'm going to talk about what we call the Hopfield barrier, and this goes back to John Hopfield. I'll tell you a bit about him in a moment. I'm going to spend a little while telling you about the mathematical machinery that we use to study these problems. We call it the linear framework. And one of the results that's emerged from this is the idea that the Hill function, that I'm sure all of you know, you've come across, has an interpretation from an unexpected point of view as a Hopfield barrier, and I'll explain what that means. And depending on how much time we have, I'll explain how it is that we can make a very powerful statement about the Hill function here as a sort of universal barrier. And I'll try and explain where that universality comes from. And then finally, again, depending on how much time we have, I'll tell you a little bit about the challenges that we face in trying to follow the energy. Okay, so that's the plan. And let's start off with Hopfield. That's John Hopfield, shown on the right, engaging in doing some mathematics in a very nice setting.
Wow.
And back in 1974, which is now a long time ago, he wrote a classic paper. He's a physicist, and he described this mechanism that you may have heard of. It's called kinetic proofreading. And it was his way of explaining how biology is able to do such amazing things like replicate DNA with an error rate of 1 in 10 to the 9 or 1 in 10 to the 10. Okay. And Hopfield was trying to understand how processes like DNA replication or mRNA construction or protein translation, how these processes manage to have such incredibly low error rates. And the way he approached this, I'm sort of, this is not the language he used, I've sort of rewritten his language in a way that will fit with what I want to tell you about in a little while. And his thinking went like this. The basic way in which you discriminate in biology between a correct and an incorrect substrate is through binding. That's the first thing that you do. You bind to something. And typically what you find in biology is that discrimination between correct and incorrect happens through the off rate. The correct substrate stays longer. And so has a lower off rate than the incorrect substrate, which tends to fall off. Okay, so you get an immediate discrimination that comes about just through binding and unbinding. And if you look at what kind of error you might expect from this, just from what was known at the time about binding and unbinding, then you might expect to get an error rate, you know, of say something like 1 in 10 to the 4. That was consistent with the data that was available. So there was a real puzzle as to how it was that biology managed to attain error rates of 1 in 10 to the 9, 1 in 10 to the 10. And Hopfield reasoned like this. He said, well, if you can get an error rate of 1 in 10 to the 4 by doing one binding, why not an unbinding? Why not do 2? Okay, so now we move from the graph on the left to the graph on the right, where we imagine that the system goes through a state which allows it to bind and unbind, then moves to a different state that allows it to bind and unbind again. And you might think, well, if you can get an error rate of 1 in 10 to the 4 the first time, and an error rate of 1 in 10 to the 4 the second time, you ought to be able to get an error rate of 1 in 10 to the 8. So what goes wrong with this scheme? And what Hopfield realized is that what goes wrong with this scheme is that if this mechanism is operating without energy expenditure at thermodynamic equilibrium, then you cannot tell which of the paths you took in going around the graph. In other words, the probability of the exit state 2 doesn't depend on the path you take to get there if the system is at thermodynamic equilibrium. Now, I'm sure you're all familiar with this, but let me just remind you, because as a mathematician, this was something that I had to learn the hard way. Mathematicians use the word equilibrium to often mean steady state.
Yes.
We mean basically a state in which the time derivatives are 0. But to a physicist, that's a mortal sin, because what a physicist means by equilibrium is thermodynamic equilibrium. And a thermodynamic equilibrium is a very special kind of steady state. And I've illustrated the difference here by these diagrams. And I think hopefully this is clear to everyone. Thermodynamic equilibrium is a very special kind of steady state in which lots of important things happen, like detail balance. And in particular, you have this property of path independence. So the only way for Hopfield's scheme to work is if you introduce energy. Specifically, he suggested in the transition from state 1 to state 2. And by doing that, you break detail balance. And now the steady state probability of the exit state depends, it's sensitive to the path that you took to get there. And if you do that, then Hopfield did a fairly simple calculation and showed that you can get close to this squared error rate. And that's Hopfield's idea of kinetic proofreading. And it turns out that subsequently, we've come to see that kinetic proofreading is at work in most of the systems that we find in biology, like DNA replication and mRNA transcription and protein translation. So kinetic proofreading is sort of a fundamental idea that Hopfield introduced into biology. Now, going back to this paper and rereading it again, we realized that actually Hopfield was telling us something even more significant than what he said in his paper. And I think what he's telling us is something much more general. And what it is that this insight is true for any information processing task. It doesn't have to be the one of discriminating between a correct and incorrect substrate. It could be anything you want. It could be classifying, it could be sorting, it could be learning, it could be amplifying. It doesn't matter what it is, whatever information processing task you have in mind, that there's always a fundamental upper bound to how well you can do it at equilibrium.
Mm-hmm.
And the only way you can get past this is to introduce energy and take the system away from thermodynamic equilibrium. And this fundamental upper bound is what we call the Hopfield barrier in Hopfield's honor. And this set us on the task of sort of going back into molecular biology, looking at information processing, and trying to understand Hopfield barriers, and trying to determine what they were. Okay, so I think this is the really important implication of Hopfield's paper. And what I want to discuss with you is a particular Hopfield barrier that we came across, which is related to the Hill function. So that's the plan. And by the way, please interrupt if there's something that you want to clarify or have a question. Don't hesitate to interrupt, please. Okay, so that's the Hopfield barrier. And so let me tell you a little bit about the mathematical machinery that we use to study these problems, because perhaps that might be interesting in other contexts. We call it the linear framework. And it's related to those kind of pictures that I showed you a few slides ago, which were to illustrate what Hopfield was talking about. Hopfield didn't use those pictures. He sort of argued in a different language. But the pictures are really very useful, and they're very useful when you treat them mathematically as graphs. So this is what we're going to do. How the linear framework is based on finite graphs with directed edges. So these are directed graphs, and labels on the edges. And just for the moment, let's just think of this abstractly, and we'll see some more concrete examples in a bit. But the way to think about this, scenario is that a label-directed graph gives rise to a dynamical system. And it's a very simple kind of dynamical system. And I can sort of explain it by saying that it's one-dimensional chemistry. And what do I mean by that? I mean that we treat every edge, every transition in the graph, as if it's a chemical reaction. And we take the label as the rate for mass action kinetics. Okay. So it's very simple. And each of these reactions, chemical reactions, has only one substrate, right? Because every edge has only one source. And therefore, it's clear that the dynamics is linear. Okay. So it's just a series of linear equations. And therefore, I can express it in matrix form. And if I do that, the matrix that I get is something that in graph theory is called the Laplacian matrix of the graph. And from this, you can unwrap exactly what it is. For the example that I've shown there, I've shown the Laplacian matrix just below the graph. And I think it's fairly easy to see how you get that from the one-dimensional chemistry. So this is a very straightforward linear differential equation. There's nothing complicated about it. One thing I might note is that there's a conservation law, because if we imagine doing one-dimensional chemistry on this graph, all we're doing is moving material over the edges. We're not creating material and we're not destroying material. And so the total amount of material has to be constant. And so there's a conservation law here. And the conservation law corresponds in matrix terms to the column sums of the matrix always being 0, as you can see from the example. Yeah. So all this looks like a game, okay? It doesn't look as if it's even related to something interesting. But it turns out that with this, you can actually do quite a lot of interesting biochemistry. And originally what we were interested in doing was looking at post-translational modification systems, which are enzyme-catalyzed biochemistry. And the key point here is where the labels are coming from in the graph. Because the labels in the graph basically encode how that graph interacts with its environment. And so in this context of enzyme-catalyzed biochemistry, what happens is that the labels on one graph are derived from the vertices in another graph. And although the system we're starting from is very nonlinear, this graph trick allows you to break it apart into a set of linear dynamics operating on these graphs, which are coupled together in a nonlinear way. Okay, so what you can do all sorts of very interesting things with this and prove some nice theorems about what happens in post-translational modification systems. I just wanted to sort of point this out because this is actually a very powerful way to use this machinery. But what I'm going to talk about for today is actually in somewhat a more limited context. The more limited context is when you make a very drastic simplification about where the labels are coming from, and you only have one graph to worry about. So we'll move on to that, but you can use this in a very different way if you want to look at biochemical systems which are enzyme catalyzed in this way.
So, Jeremy, I have a question.
Please.
Yeah, a while ago I read this paper, so I remember the main idea. So what I understood is following. If you have a non-linear dynamics, for example, bimolecular combination or the reaction, then you can bring one variable out of two and make it a rate constant so that you can make the nonlinear or the quadratic kinetic into linear kinetic in that sense. Is it correct understanding or?
Yeah, but the difficulty is to do this in a consistent way when you have a system of reactions, right?
I see.
And what the framework allows you to do is to do this in context like this, where we're dealing, for instance, with enzymes that are catalyzing reactions on substrates. It's not the case that you can always do this peeling apart of the labels to separate, if you like, the linear from the nonlinear, right? That's the key trick. But in the context of these post-translational modification systems, you can do that very successfully.
I see.
Thank you.
Okay. So what I want to move to is a simplified context, because this actually connects to something else, which is Markov processes. So now we're going to imagine that we're dealing with a situation where the labels encode relationships with the environment. Typically, they're binding and unbinding relationships. But these things in the environment are in reservoirs. And I use the word reservoir. If you're familiar with thermodynamics, you'll know what a reservoir is. A reservoir for our purposes is something, a container for molecules where if you take a molecule away from it, the chemical potential doesn't change. And the way you should think about this in thermodynamics is a heat reservoir is something when you take heat from it or give heat to it, its temperature doesn't change. And so this is the equivalent concept in the chemical world. So we're assuming that the things that bind and unbind, their free concentration doesn't change. So this is a much more limited context, a more stringent abstraction. But what's interesting about it is that in this context, what the graph describes is a Markov process. And the relationship between the Markov process and the graph is sort of explained in the box on the right. If we have a Markov process X, so we imagine a finite number of states, and it has the usual, this is a continuous time finite state Markov process. What the labels in the graph are simply the instantaneous transition rates. And if you have any Markov process for which you have instantaneous transition rates, you can make a graph. And if you have a graph, you get a Markov process. So the graph is just another way of doing Markov processes. Now, in the Markov process world, you very rarely see this graph. But it turns out the graph is extremely useful. And I'll sort of try to explain why that is. But in this context, where we've made this assumption that the environment is simplified, as it were. We're not dealing with things that are doing other things in the environment, like a complicated enzyme mechanism. They're just going into their reservoir and coming back. So in this context, we have this very nice relationship between the graph and Markov processes. Okay. All right, so in that context, the equation that I wrote previously on the previous slide, this linear equation has a very nice interpretation. It's the master equation of the Markov process. Okay, that's the equation that tells you the forward evolution of probabilities for the Markov process. And so what in the Markov process world would be called the master equation, we think of as this linear Laplacian dynamics on the graph. Okay, so why go through all this? Why, instead of just looking at Markov processes, why do you have the graph? What's useful about the graph? And the point is that the graph gives us algebraic access to steady states. And the way that works is through a classical piece of graph theory called the matrix tree theorem. Okay. So what we want to do is to calculate the steady states of the Markov process, which I've indicated in the bottom as pi asterisk. The asterisk is to say we're at steady state. Okay. So we want to know the steady state probability for one of these graphs at vertex I. And we can work that out completely algebraically using graph theory. And the way you do it is, well, what's a steady state? It's essentially where the derivative is 0, so it must be an element, a vector in the kernel of the Laplacian matrix. And it turns out that provided the graph is strongly connected, what does that mean? It means that if I take any two vertices, there is a directed path from one vertex to the other. And because I've chosen them arbitrarily, there must be a directed path from that vertex back. Okay, so that's strong connectivity of a directed graph. So as long as the graph is strongly connected, the kernel of the Laplacian is one-dimensional. And I can write down a canonical basis element for it in the formula that I've shown you there. And I'm sorry, I should have added some graphs to explain this, but let me try and just unwrap this for you because it's a very beautiful formula, speaking as a mathematician, but we'll see it conceals a lot of interesting complexity. Okay, so how do I construct this basis element at vertex I? Well, what I do is I look at the spanning trees in the graph that are rooted at vertex I. What's a spanning tree? It's a subgraph which has every vertex in it. That's what it means to be spanning. And it has no cycles if I forget the edge directions. Okay, that's what it means to be a tree. And finally, it's rooted at the vertex I if there are no outgoing edges from I. So you imagine the sort of tree, it's more like it's hanging from the root. So if I take a tree T of that kind, it's a spanning tree of the graph rooted at I. I look at all the labels on the edges and multiply them together. And then I add all those things up over all the trees. That's what that formula is saying. So if you give me any graph, that's a very simple way of describing this element. It's the sum of products of labels over trees. That's it. And that is a canonical element in the basis of the kernel of the Laplacian. It's a canonical element in the kernel of the Laplacian. And as a result of that, we can easily write down what the steady state is by just normalizing it, because of course, the sum of all elements of probability is 1, right? So it's easy to normalize.
Oh, so there was a question in chatting room. Could MTT be related with the condition of detailed balance?
Excellent question, which I'm going to talk about on the next slide.
Cool.
Okay. So this is true in general for any graph. But Jay just asked a very relevant question, which is what happens if the graph is at thermodynamic equilibrium? So if that's the case, what does that mean in the graph context? So what it means is that detail balance holds. That's the condition for being at the thermodynamic equilibrium. And what does detail balance mean? Well, first of all, we've got to ensure that this graph is reversible. And by that, I mean that if I can make a transition from state I to state J, I must be able to take the reverse transition from J to I, right? There's no irreversibility. It must be reversible. And it's not just that you can go back from J to I, you have to actually be going in the reverse transition, right? That's important. So first it has to be reversible. And then if I take a pair of these reversible edges, then that pair of edges is sort of independently in flux balance. If I take the steady state probability of this vertex and multiply it by the transition rate to get the flux that way, that's equal to the steady state probability of this vertex multiplied by the transition rate going this way. The flux is balanced for every pair of reversible edges. This is detail balance. It's kind of amazing. The whole graph basically falls apart into these balanced edges that are just connected by the probability distribution. So that's what detail balance means in this case. And now what happens is that you can get a completely different basis element in the kernel of the Laplacian. And this basis element is very different from the one I described. And it's in fact much simpler. So if I want to describe this basis element, what I do is I choose some reference vertex in the graph. It just could be anything. We call it 1. And if I'm computing the basis element for vertex I just take a path of reversible edges from I to 1. It can be any path. And then I take the product of the ratios of the labels along the path, and that's it. And the first thing that will probably occur to you is, well, what happens if I take a different path? And the answer is that detail balance ensures that it doesn't matter what path you take, you get the same answer. And this is what I meant when I was talking about Hopfield's kinetic proofreading, that at thermodynamic equilibrium, we have this property of path independence. Steady state probabilities don't depend on the path you take. This is what it means mathematically. And that ultimately comes back to detail balance holding. And I haven't sort of gone through the derivations here of showing why detail balance implies this, but if you think about it for a little while, I don't think you'll find it hard to see why it is that detail balance implies that this quantity mu ij is independent of the path chosen.
Yes.
Yeah, I mean, I think you can almost see it. It means if you take two different paths and go around them, you're not going to generate a cycle. That you can't generate flux around the cycle. That's basically what it's saying. Yeah. So this alternative basis element is very interesting because it immediately relates to what we know in thermodynamics. So in thermodynamics, what we know is that when we have a system at equilibrium, we have a free energy. Okay, and how the free energy is related to the labels is also very understood. It's a kind of Van 't Hoff formula, and it basically says that these label ratios are basically related to the free energy difference between the states. And that's sort of basic thermodynamics. And if you put that into the formula for the steady state probabilities, what you recover is precisely equilibrium statistical mechanics. So in answer to Jay's question, is that when you have a graph that satisfies d-tau balance and is therefore at thermodynamic equilibrium, basically you recover from the formula that I showed you, the matrix tree formula, you recover equilibrium statistical mechanics, basically. That's the answer. So, this machinery, when you're at equilibrium, it agrees with equilibrium thermodynamics. But the really important thing about it is that it holds away from equilibrium, because away from equilibrium, the matrix tree theorem still tells you how to calculate the steady state probabilities. And that's really, really nice, because in context outside this, we basically don't know how to calculate steady state probabilities away from equilibrium. It's an unsolved problem in non-equilibrium statistical mechanics, is still an unsolved part of physics. There's been a lot of important progress, fluctuation theorems, all of that. But in terms of calculating steady state probabilities, there's no general method to do it. But in this garden, where we're working with these graphs and Markov processes, we can do it exactly. And that's what makes this so useful for studying, for following the energy. So I'm sorry if that was a little bit rushed, but I've given some references for those who want to pursue it further. I'm happy to answer questions if anyone wants to raise anything now. But let me just say, I'm going to skip over these slides, that what I've said today is actually connected to lots of branches of mathematics and physics. I've sketched some of them here. These are all independent kind of reconstructions of some of the things I've been saying. And what we've been trying to do is to sort of draw all of this knowledge together within the linear framework and exploit it. And I think the thing I would say that makes the approach we're taking a little bit different from some of the things that people have done with graphs in the past is that we treat the graph as a mathematical object. It's not a picture for us. It's something about which we can prove theorems. And that's my mathematical past that still lives as a biologist. Okay, I like the idea that we can prove theorems about biological systems. And this graph theoretic machinery allows us to do that. Okay, I don't want to sort of spend a lot of time on this. I just wanted to sort of mention this as one of the reasons why we like using the framework.
Jeremy, I have a clarifying question.
Please.
Yeah, so in your path L from I to J, so I and J are not the entities or items on your graph, right? So I and J is a microstate, a configuration of your many items on your graph.
No, I and J are vertices in the graph.
Okay.
So the graph.
I thought I and J is a microstate or configuration.
No, they're vertices in the graph, and the vertices can represent whatever you like. I haven't sort of specified the level of abstraction at which the graph is being formulated. So they could be configurations of some system, or they could be, for instance, states of binding of a system. The graph is really abstract, and it's up to you how you want to interpret the vertices, and we'll see different examples. But what I'm on these slides, when I use I and J, I'm referring specifically to vertices in the graph. And when I talk about paths, they're paths in the graph.
So vertices on your graph does not represent the chemical component then.
They could.
It could, okay.
Yeah, they could.
Okay, I see. Thank you.
Yeah, so in that case, what's the meaning of the probability P sub I if I represents chemical component?
It depends on the kind of system that you look at, but you imagine that whatever system that component is in, it has reached a steady state, and then you're asking for the probability of that state being present.
I see.
Yeah. So in the Markov process context, we're often looking at the example that I'll sort of run with here is the example of gene regulation. So in this case, we typically think of the graphs as being sort of states of binding on DNA. So a vertex represents a transcription factor that's bound here, another transcription factor that's bound here, something else bound there, chromatin in this configuration, nucleosomes here. It doesn't matter what the level of abstraction is. It could be very complicated. It could be much more abstract. But that's the state of the system at some level of abstraction. The edges are sort of transitions. They occur when things bind or unbind, or some configuration changes. There's a conformational change, something like that. And so in that context, we can ask for the probability of this state at steady state, or the probability of this state at some time t.
Okay, so can I ask one more question? Suppose you have a non-Markovian process. Then
sorry, say again, I didn't hear that.
Yeah, suppose you have a non-Markovian process. Then how can you represent it as a graph? Or you cannot represent the non-Markovian process at all with a graph at all?
Correct. In this interpretation, we're doing Markov processes, and if the system has some non-Markovian aspect, then you'd have to unwrap that. You know, maybe there's some history in that where you can unwrap it into something Markovian, in which case you could use the graphs. But if it's non-Markovian, this doesn't cover it.
Okay, I see.
Okay.
So Markovian, this is coming from the fact that your reaction rate only depends on the entity at the end of one arrow in your graph, right?
So I don't know quite whether the question is about the graph or the question is about the context that is being modeled. I think we're making the assumption that the rates in the context we're being modeled depend on the state, not on the history that you took to get there. Yeah. Does that help?
Yes, I think I understand. Teacher means that suppose you have an arrow. Arrow is representing the reaction on your graph, and then that reaction rate depends on only one of the items connected by the edge or arrow.
Correct. Correct.
Okay. That's an interpretation of your Markovianness.
Yeah. We'll see an example in a couple of slides, which might make it a little bit clearer. Okay. So let me try and tell you then a little bit about the Hopfield barrier here that we're interested in and how the Hill function appears. What we want to do is to look at the sharpness of binding. So binding is one of, as Hopfield pointed out, is the sort of basic process. It's the basic mechanism through which information is processed. So if you imagine a gene and a gene being regulated to make mRNA, ultimately where that starts is with the binding of transcription factors to the DNA to recruit other machinery, to change chromatin, to bring the polymerase, and to start the process of mRNA transcription. So what we were interested in is how binding integrates information. Okay, and so to do that, we started to look at the question of sharpness in binding, because the sharpness of input-output functions that arise from binding. Let me talk further, and then rather than show you some slides, because it'll be clearer then. Okay, so we're going to look at the issue of macromolecular binding, and I'm using this running example here, which is actually an example of gene regulation, as you can see, but it doesn't have to be the regulation of a gene. It could be any macromolecular system. It could be complicated. It basically is interacting with things that bind and unbind from it. Right. And in this example, which is that of a gene, we imagine that we have sites of binding, two sites of binding for a transcription factor, which is the blue oval, and another site of binding for something which you can think of as the polymerase, which is a complicated thing, but we imagine that it's got its own promoter binding site. And this is a very typical way in which gene regulation is studied. Okay, we want to understand how the binding of transcription factors influences the probability of recruitment of the RNA polymerase and the processing of mRNA. So in this kind of graph, I haven't given the labels here, but you can imagine that these labels are now related to the concentrations of these transcription factors and their off rates and so forth. So in this kind of system, we can describe input-output functions. And these input-output functions are basically linear combinations of steady-state probabilities on the graph vertices. And we imagine that we're going to look at that function as, look at that output as a function of one of the things that's binding to this macromolecule. And I'm going to call that L and call the concentration of L X. So there might be lots of things going on. There might be nucleosomes. There might be other things that are floating around and binding, and unbinding could be very complicated. There could be conformational differences and so forth. So the graph could get very complicated. This is just an example of a graph, just to keep it in one's head. But we're going to be looking at these input-output functions. That's the basic machinery that we want to look at. And we want to look at particularly this question of sharpness. And by sharpness, I mean, if I change X a little, by how much does the output change? That's basically the question of sharpness. And we use words like ultrasensitivity and things as ways of talking about sharpness, but I want to sort of approach this from a more mathematical perspective, okay?
Here, lambda is depending on the X, right?
Here, no, the lambdas are not depending on the X. These are just coefficients that are attached to vertices. So they're weights on vertices. Okay, it's saying that, so one very simple weighting that I think perhaps makes sense in this context is to ask for the probability of polymerase being bound. Okay, now what would the weighting be there? It will be 0 on all vertices where polymerase is not present, and it will be 1 on the vertices where polymerase is present. So that would be a typical input-output function that we actually look at in the context of gene regulation. It's the probability of polymerase being recruited. Okay? But the coefficients
which term is depending on X for f of X?
Sorry, I beg your pardon, I couldn't hear that.
Sorry, so which term in f of X depending on X?
It's the steady state probabilities, and it's through the formulas that we looked at here, because these steady state probabilities are given through the matrix tree theorem by this rational function, and the terms in that rational function are described by the matrix tree theorem as sums of products of labels in the graph. And the X is the concentration of the things that are binding on the graph. So the X appears through that.
I see.
Okay, so these PI star terms are potentially very complicated because you have to unwrap these formulas, but that's where the X is coming from. Okay.
Thanks.
Okay, so we're going to look at these input-output functions, and I hope you get the sort of general idea. This could be a very complicated situation where you have binding of many things, of conformations, changing transitions, but we're focusing on one of the binding elements. We call that L, and we're looking at its concentration X. And what we're asking is, how does this output, which could be any linear combination of steady state probabilities, how does this change with X? That's the basic question. And particularly we want to look at this question of sharpness, because in the biological context, that's something that's actually quite important. So we're going to measure sharpness. People do it in lots of different ways, but we're going to do it in a very particular way, which is more intrinsic and mathematical and turns out to be very important. First of all, we're going to normalize everything. So if you remember this slide, you will see that this function is already normalized because these coefficients are assumed to be between 0 and 1, and these are all probabilities, right? But we're also going to normalize the independent variable, and we're going to do that in a way that actually comes from what people do in the experimental context. We're going to normalize to the half maximal value.
I see.
Okay. And that's actually kind of a subtle normalization because it depends on the function, right? But we normalize to the half maximal value. That gives us a completely non-dimensional function. And then we're going to estimate its sharpness with two quantities. And it's very important that we do this with two quantities. The first quantity is the maximum of the derivative, and we call that the steepness. And the other quantity, we used a really silly name for it. We call it the position. And it's just the normalized value where the maximum occurs. Position and steepness, that's it. Okay, I mean, this is very straightforward, but this is the way we're going to measure sharpness. Okay, so now what I'm going to show you is a plot of position and steepness. And there's this next slide, I'm afraid, is a little heavy. So bear with me and I'll try and explain what's going on here. Okay. So what you see in the center there is a plot of position and steepness, normalized position, normalized steepness. It's for a particular model. It's for basically the model I showed you on this slide, except now there are 6 binding sites, plus a site for polymerase. So we were thinking about gene regulation here. And there's actually data on that slide that I'll talk about. So this is for a particular, we were trying to model a particular gene. And the gene is actually called hunchback. And it's a gene in the early Drosophila embryo, in the development of the early Drosophila embryo. And we're interested in how hunchback is regulated by a transcription factor called bicoid. Okay. So if you're familiar with Drosophila development, this is a very canonical and important gene. We're not going to sort of discuss Drosophila development here, but that's the example that we were trying to model. And it's known that hunchback has 6 binding sites for bicoid. So that was why this model that we're working with has 6 binding sites plus the polymerase. And the input-output function we're looking at is exactly the one that I described. It's the probability of the polymerase being recruited. Okay? So that's the input-output function. Okay, so what we're plotting here in gray is the position and steepness of all such models at thermodynamic equilibrium. Okay, so how do we get this region? Well, basically we do random sampling of parameters for the labels. That gives us an input-output function. We plot its position and steepness. And then we have algorithms that grow that region until it won't grow any further. And this is actually very delicate numerically. It requires not only growing out, but also trying to get over the boundary and until you sharpen the boundary. So I'm not going to go into the numerics. This took several years to get right. But one of the things we discover is that if the graph is at thermodynamic equilibrium, then the position steepness points fall in this finite region of the space. Now, we're truncating to the left and the bottom because there's other stuff that happens here, so don't worry about that. But the region is this strange cusp-shaped region. And what you find is if you let the parameter range increase, then this region sort of moves apart and then stabilizes. And what I'm showing you here is the sort of asymptotic boundary. And what's interesting about this boundary is that if you look at this cusp falls on this blue line. What is the blue line? That's the position and steepness of the hill functions. And what you see is that the apex of this cusp is very close to the hill point with coefficient 6. And when you increase the parameter range, that tip of that cusp gets closer and closer to hill 6. Okay, so what this is saying is that if this graph is at thermodynamic equilibrium, its position and steepness can never exceed that of a hill function with coefficient 6. It's trapped in this cusp. Okay, so let me tell you what happens when we're not at equilibrium,
Mhm.
because that is what we need to confirm that this is actually a Hopfield barrier. What I'm showing you is that there's a barrier here. The question is, but suppose I'm not at thermodynamic equilibrium. Do I get past this barrier? And the answer is yes, but if I want to show you a region, then I have to come back to 2 binding sites in polymerase. And this is a plot of what happens for 2 binding sites in polymerase. And you might ask me, why 2? Why not 6? And that's where there's another story to tell, which I hope I might tell you in a couple of slides. But what happens for 2 binding sites is that at equilibrium, again, you get this region, which has a cusp at hill 2. And when you're away from equilibrium, still with just 2 sites, then your position and steepness can increase at least as far as hill 4.
I see. I see.
And we know, we can't plot the regions, but we know that exactly the same is true for 6. That is, we can find away from equilibrium things that exceed the Hopfield barrier. So this is where this idea that the Hill function is a Hopfield barrier begins to emerge. Okay. Now, I want to tell you very quickly about the data points, because what these points are actual data from actual embryos. Each point is a Drosophila embryo, where we've done the microscopy to estimate this input-output function and measured its position and steepness. We've done this for two different constructs, which are shown at the bottom. The one that's important here is what's called the synthetic construct, because in this synthetic construct, what we've done is basically to make sure that nothing else is binding except for bicoid. So that this construct is as close as we can get to the model that we're actually using. Okay. The wild type, the actual enhancer for Hunchback, has other things that combined, which we're not actually modeling here, right? So the purpose of this synthetic construct is to make something that's as close to the model as it can. And you'll see that the position steepness is very interesting. It's clustered around the Hill coefficient 6 site. Some of the points fall within the region, some of them fall outside the region. And so it's very ambiguous. It's hard to say whether, the data are accommodated by the model or not. Some of the data is, some of the data is not. So it's sort of ambiguous. But what happens if you now do some deletions on the construct, and that's shown in the insert, if you take out 3 of the sites, then what you notice is that the equilibrium region is very far away from where the data is.
I see.
So this is telling us that we cannot account for this data with a model of gene regulation that's at thermodynamic equilibrium. And what's interesting for me about this is that we can say this without fitting any data. Right? I mean, I know we were talking with one of your students who's struggling with the problems of parameter fitting. I know what those problems are like. I hate that. and what I like about this is that we don't fit any data, but we can still make a strong comment. The strong comment is that this data cannot be explained by this model. It doesn't matter what the parameter ranges are because this is an asymptotic boundary.
Right, I see.
Okay, so this is the starting point for this idea that the Hill function is somehow a kind of limit of what you can achieve in the way of sharpness for systems at thermodynamic equilibrium.
I see.
But there's a problem here because this region is the region for a particular model. It's this model, right? And you could easily come up and say, but hang on a minute, but suppose now we have a more detailed model. Perhaps we put nucleosomes in, perhaps there are conformations that are changing. What happens to the region then? It's a different region. Maybe that region could accommodate the data. Maybe it's just that you haven't put all the details into the model. And that's a serious objection. But it turns out that actually something really we were surprised about, which is that there's a universal region
Mm.
which accommodates all models. Okay. So I notice we're creeping up to time here, Jay, and I don't want to take us beyond time, but I can say a few words about this universality.
Please, okay, yeah, please go ahead. Yeah.
Thank you. Okay, so we were doing a different piece of work. We were studying allostery, and during the course of doing this, we developed a method using the linear framework for what we call coarse graining.
Mm.
And this is a way of taking one graph and making it and coarse graining it, basically. And I should say immediately, because this coarse graining problem is very interesting, that this coarse graining is at steady state. We're not coarse graining the dynamics. We're just coarse graining the steady state, okay, which is a much simpler problem, but still a useful one. And this coarse graining technique allows us to make this universality claim. And I want to explain how that works.
Mm-hmm.
So suppose I start with a graph G, which could be arbitrarily complicated.
Mm-hmm.
Okay, I'm just giving an example here. It involves the binding of something that we're interested in, the blue element, but it could have all sorts of other things.
Mm-hmm.
Other things that are binding, other conformations, all sorts of other transitions. It can be as complicated as you like. I can always coarse grain that in the following way.
Mm.
In general, the way this coarse graining works is I can take any partition of the vertices in this complicated graph. So I've taken a particular partition here, but it could be any partition of the vertices. And I remind you, a partition are subsets that are disjoint but cover the graph.
Mm.
Right? And now we can construct a new graph in which the vertices represent the subsets. Okay.
I see.
And we can make an edge from one of these subset vertices to the other subset vertex if, in the detail graph, there is some edge from within that subset to within that subset.
Mm-hmm.
That's it. Okay. And let's think about how that would work if we coarse grained in the following way.
Mm.
So I have this very detailed graph.
Mm-hmm.
And I'm going to coarse grain it by looking at all of those subsets, all of those vertices, which have exactly the same pattern of binding of the ligand.
Mm-hmm.
So in this case, there are just 4 subsets because the ligand is binding at 2 sites, and therefore it may not be bound at all. It may be bound at site 1.
Mm-hmm.
It may be bound at site 2.
Mm-hmm.
It may be bound at both sites.
Right.
So we get 4 subsets, and you can easily see that because there must be binding and unbinding, what we recover is basically the binding graph, the edges and the vertices, for binding to just 2 sites.
Mm-hmm.
Now
the question.
Yeah.
So this might be a very technical question, which might not a major issue, but if you merge these states into a partition, I think we lose the Markovity.
But we're not looking at the dynamics.
I see.
You're absolutely correct. You're absolutely correct. And that is the great challenge of doing coarse graining.
Mm.
But we're not looking at the dynamics. We're looking at the steady state.
Correct. Okay.
Now, the key point here is that I've told you about the vertices and the edges, but the key point is that we can find labels for this coarse grain graph such that the coarse grained linear framework graph satisfies this coarse graining equation. And the coarse graining equation is basically very straightforward. It says that if I look at the probability in the coarse grain graph, what I get is exactly the probability of being in that subset in the detailed graph. That's just unwrapping that formula that you see at the bottom there, okay? And there is, so I should say that this way of giving the labels always gives a graph at thermodynamic equilibrium. So the detailed graph may be away from equilibrium, but this coarse graining procedure always constructs a graph that's at thermodynamic equilibrium. And if you impose those two conditions, that is to say, the graph must be at thermodynamic equilibrium and the coarse graining equation must be satisfied, that's essentially the only way to assign the labels. So this is a unique procedure. Now, there's something kind of interesting here, because what this tells you is that you can't tell whether a graph is at equilibrium or away from equilibrium by looking at its steady state probability distribution. Because if you give me a non-equilibrium graph, I can construct an equilibrium one with the same steady state probability distribution. Okay. But let me not take too much time up here, but this is the starting point for this universality procedure, because you see, if I start with an input-output function on the detailed graph, I can now convert this into an input-output function on the coarse grain graph, and we're really dealing with conditional probabilities here, and the formula is actually quite straightforward when you unwrap it. But the key point is that if the detailed graph is at thermodynamic equilibrium, then the coefficients that I get in the coarse grain graph don't depend on x, don't depend on the independent variable that I'm looking at. If they are away from equilibrium, they absolutely can, but at equilibrium they don't, and therefore, and this goes back to a question that Junsu asked, this input-output function, this function that I've written down on the coarse grain graph, is a proper input-output function. The coefficients don't depend on the independent variable. So you see what we can do, we can start from any arbitrarily detailed graph, take any input-output function on it, and we can convert it into an input-output function on this simple binding graph. And now, if I want to understand the position steepness of the very complicated function, I just have to look at the position steepness of this function on the coarse grain graph, but I have to allow the coefficients to vary, because it's the variation of the coefficients that captures what's going on in the detailed graph. So if you unwrap all that, what it turns out is that there is a universal boundary. There's a universal region in which the position steepness of any model at thermodynamic equilibrium must fall. And it has exactly the behavior we were expecting, namely that it too is bounded by this Hill coefficient, 6, for 6 sides. So this is where we get this theorem. It's not a proper theorem because all of what I've told you is numerical. We don't have a formal mathematical proof of it yet. But I think we're absolutely convinced that this is correct. The Hill function is this universal Hopfield barrier for sharpness.
So when you say any model, which means any gene regulation model or any biology model?
Any model of macromolecular binding. So we can have binding of other things, we can have conformational changes, whatever you like. Yeah. All that matters is that you're focusing on one thing that is binding. And looking at the relationship of the function with that one thing. Everything else is constant, but that one thing is the thing that you're looking at.
I see. Okay, gotcha.
Okay, so I've taken up a lot of your time. So I'm going to, I'm sort of going to pull, I'm going to stop there because we would get too far afield if I went further. But if you'll excuse me flipping through a few slides, I just want to say thank you to some of the people who've been involved in this.
Please go ahead, yeah.
A lot of this work was done in collaboration with my department colleague, Angela De Pace, who's the Drosophila genetics person who provided the data that I showed you. And it actually came from a postdoc in a lab called Ji-Hae Park. And these are some of the people in our labs who have contributed to building up this story. And I won't go through and tell you all of the things that they did, but they are particularly responsible for the things that I've discussed with you today. And these are my lab and some of the people who've contributed over the years to the development of the linear framework. So I'm really sorry for exceeding my time, and I'm again very sorry for the confusion about the times. But thank you very much for your attention. I'm more than happy to answer any questions if you want.
Wow. Thank you. Wow, very interesting. So, any questions from audiences? Please feel free to unmute yourself and then ask the question to the speaker.